Now we're given a force of 2 newtons, that's exerted at a position 5 centimeters from the axis of rotation of a 30 centimeter rod having a mass of 80 grams. And that's very close to the straps that we've used in class and that you've seen demonstrated. Reasonably close, I wouldn't say very close. So here's a depiction. At a point 5 centimeters from the axis of rotation. Here's the axis of rotation. And here's, I've drawn this as a 5 centimeter displacement vector from here to here, from the axis of rotation to the point at which the 2 Newton force is exerted. The 2 Newton force is exerted perpendicular to the rod, therefore perpendicular to this displacement vector. Now, this displacement vector, we can give it a name. We can call that the moment arm of this force. We're asked, what's the angular acceleration of this rod as a result of this force exerted at this position? Well, what accelerates a rotating object it's the torque that we apply to it. So we have the relationship torque equals moment of inertia times angular acceleration, the analog of Newton's second law. Force equals mass times acceleration. Well, that's for objects that are moving from one point to another in space. For things that are rotating, it's torque instead of force, it's moment of inertia instead of mass, and it's angular acceleration instead of acceleration. Acceleration accelerates you from here to there, or changes your velocity in a direction from here to there. This doesn't change your velocity, it changes your rotation, and rotational velocity or angular velocity. Okay, well, the key is then that the torque is moment of inertia times angular acceleration. We can calculate the torque of this force, and that's very easy. We just calculate the 2 newtons multiplied by the moment arm, the force multiplied by the moment arm. That works as long as the force and the moment arm are perpendicular, which is the case here. So torque is 2 newtons times 5 centimeters, which is 2 newtons times 0.05 meters, which is 0.1. Now you could say that's a Newton meter, but a Newton meter sounds a lot like a joule. There's a connotation there of work and energy, and that's not what's going on here. This is essentially a type of force that is used to rotate things, and that's not a very precise analogy. Well, it's a good analogy, but the terminology is not really precise there. But you get the idea that this is what rotates the thing, and it's not an energy or a work. It's something that produces work and requires energy. Well, instead of calling this a Newton times a meter, which feels like a joule, a unit of energy, we call it a meter times a Newton, just to keep reminding ourselves that this is a torque and not some amount of work or energy. Okay, so it's 0.1 meter newtons. Now, we want to find the angular acceleration. That's really what we're after. To do that, we need to find the moment of inertia. We now know the torque. We've got to find the moment of inertia. Well, I gave you the formula that applies to this situation. This is a rod rotated about its center, so its moment of inertia is 1/12 ml squared, where big M is its mass and big L is its length. We can calculate that very easily because you're given its length, which is 30 centimeters, and you're given its mass, which is 80 grams. Now, the mass of 80 gram mass, I'm going to express in kilograms. It's 0.08 kilograms, and the force is, the length is 30 centimeters, which is 0.30 meters. So we're going to do 1/12 of 0.08 kilograms times 0.30 meters quantity squared. I equals 1/12 ml squared. And when we calculate that out, I believe you get 0.0006 kilogram meters squared. 0.3 squared is 0.09. 0.09 times 0.08 is 0.0072. 72 divided by 12 is 6, so the 0.0072 is reduced to 0.0006. Now, you take your calculator and figure that out, or use a multiplication algorithm and count your decimal places very carefully and see if that corroborates. In any case, if this is correct, then because torque is the product of moment of inertia and angular acceleration, the angular acceleration is going to be torque divided by moment of inertia. This should be an intuitively appealing calculation. Appealing isn't quite the right word, but I'm not finding the right word. Because just like if you have a force and a mass, you're going to divide the force by the mass to get the acceleration, and hopefully you're very used to doing that, and that fits very well with your intuition. Well, in this case, the torque is like a force, analogous to a force. The moment of inertia is analogous to a mass. So it makes sense to divide the torque by the moment of inertia. Also, more torque is going to give you more angular acceleration. Greater moment of inertia is going to give you greater resistance to acceleration. So a greater number in the denominator is going to give you less acceleration, which is exactly what a greater moment of inertia would do. Greater torque being in the numerator would give you a greater angular acceleration, which is exactly what we expect. In any case, this should be fairly accessible in an intuitive sense, and also, of course, as an algebraic rearrangement of this expression of Newton's second law. And this is, in fact, an alternative expression of Newton's second law. So we do the division, and we end up with 167. 1 divided by 0.0006 is 167. And I'm claiming this is in radians per second squared. Now, you work out the units. A meter divided by a meter can give you a radian, okay? And then that leaves us still a meter in the denominator. A newton is a kilogram meter per second squared. We divide by a kilogram, we then have like a meter per second squared, but that meter is divided by the meter, and we're just left with radians per second squared. I'm not going to go through all those details. I have in a number of other calculations, but you should work that out. And the one thing you need to understand is this meter divided by one of these meters is like a meter of arc divided by a meter of radius. It gives you a radian. Okay, well, what is the implication of this? From rest in half a second, that tells you that the rod will change its angular velocity by how much? Well, in half a second, at 167 radians per second squared, the change is going to be delta omega 1/2 second multiplied by 167 radians per second squared. And the squared is, not sure if that went off the edge of the board or if I just failed to write it. But it's a radian per second squared here, multiplied by the second, gives you a radian per second, 84 radians per second. So we would achieve an angular velocity of 84 radians per second, applying a 2 Newton force at a distance of 5 centimeters from the axis of rotation of this rod.